The derivative form of the fundamental theorem of calculus is a fairly easy topic. This is going to be a fast presentation. Basically, we have to remember one formula, one concept, which can't be that bad, but let me warn you, this is easily forgotten because for most of calculus, we're not going to use the fundamental theorem of calculus in this form, because in some ways, it's even going to feel a little bit backwards, because we're going to use in this presentation definite integrals to compute indefinite integrals, which feels kind of strange because after all, definite integrals with all those Riemann sums and all that stuff seem to be a lot harder to compute than indefinite integrals, where we just do a little bit of symbol manipulation and we get all those pretty numbers. It turns out that for more complicated functions, and especially then in applications where functions may fit a page or something like that, you can't find decent antiderivatives in terms of closed form expressions anymore. And so that's where really later on in your career this theorem will become very, very important. And then it's often somewhat embarrassing that when a teacher says, well, yeah, you've had that and you should know that, but yeah, it's been a while. So let's see what this theorem does, and yeah, that'll be all we can do at this stage. So the fundamental theorem of calculus in the derivative form says the following. If you take a continuous function, and this could be any crazy function, just has to be continuous, then the function capital G of x, which is the integral from a to x f of t dt, that function is differentiable. So this is a function of x. A is a fixed number. And what you do is you just integrate f of t from a to x, and whatever number you get there, that's your g. And the theorem says that this function is differentiable, and its derivative is obtained by just taking the upper bound of the integral, plugging it into the integrand, and whatever that is, that's your derivative. So that sort of looks like a cheap problem where we can get some points really quick, because I mean that derivative is a dream, right? Plug in the number and you got it. Let's first see why conceptually that actually makes sense, and then let us see how this theorem can be applied in fairly real situations, and how also the differentiation can sometimes get a little bit nastier. So, proof. Well, look at our function. We'll do this graphically. Here's our function f. We have that our function g is this integral that starts from a fixed starting point to x f of t dt. Starts at a, so that the function g of x just gives you the area from this a to this x. Okay, so now what happens when x changes from x to x plus dx? Well, then the area changes by something that is approximately this little rectangle here. And so that means if the change in x is dx, well, then the change in y in the g of x here is dg times f of x dx, because this little area here, this little differential in g, is just f of x, the height of the rectangle, times dx, which is the width of the rectangle. And that means that dg dx is f of x. That works algebraically very nicely, and it can be worked out with Riemann sums and limits and all that other good stuff very carefully. But for a quick idea as to why this result is true, this should pretty much suffice. Okay, so now let's see this thing in action. Let's find an antiderivative of this function, and we want to find an antiderivative so that f of 0 is 0, and we want to evaluate it at x equals 1. Okay, this function is relevant because it's what we call a standard normal distribution in statistics, so it's a function that really has quite a bit of physical meaning, and you'll see that in the statistics part of these presentations. And another thing is that because this function is so important, people were interested in its antiderivative, couldn't find one, and ultimately in the late 19th or early 20th century, a mathematician just sat down and said, look, I'm going to prove that this thing doesn't have an antiderivative in closed form, meaning it doesn't have an antiderivative that you can write down with finitely many terms, e to the whatever times whatever plus or minus correction terms and all that. So that proof, I've never seen it, but people told me it's very, very technical, because you first have to define what a closed expression is and then show that none of these expressions has this derivative. But either way, basically, this one, you just can't find a nice antiderivative. That does not mean there isn't an antiderivative. because what the fundamental theorem of calculus in the derivative form, which is what we're talking about here, what that guarantees is that every continuous function has an antiderivative. It may not be pretty, and it may have to be written down as a definite integral. And that's exactly the answer to this problem. The antiderivative of this function, or an antiderivative of this function, is the integral from 0 to x, 1 over root 2 pi e to the negative z squared over 2 dz. Why is that an antiderivative? Because by the theorem on the previous panel, to take the derivative of this integral with a variable upper bound, all we do is we take the x, plug it into the integrand, and we would get that the derivative is exactly the function that we started with. So it's an antiderivative. Does it satisfy f of 0 equals 0? Yes, because the integral from 0 to 0 of anything is just 0. And then evaluating it at x equals 1, well, you can just plug in the 1 and get the symbolic expression, and after that, look, I used a computer, and that's pretty much what anybody else can do here also, unless we specifically investigate numerical methods, which will also happen later in the course. Now, in order to get used to the fundamental theorem of calculus in its derivative form, it's good to take some derivatives that involve the theorem. So let's find the derivative of f of x equals integral from 0 to cosine of x e to the root t dt. So that is something, well, at x equals 0 you get 0, and then for a while the cosine is positive, so you don't have any trouble with the square root or so. The function ultimately is only defined from negative pi halves to pi halves, but that's not a problem so much. How do you find the antiderivative of that thing? How do you find the derivative of this thing? Now, as long as you only focus on the integral, you might be very tempted to say, hey, let me find an antiderivative here, plug in the cosine x, plug in the 0, and then take the derivative. Turns out this function is another one that doesn't have an antiderivative in closed form, and even if it did, the fundamental theorem of calculus in the derivative form is easier than to solve the integral, because here we just say the derivative of the integral from 0 to cosine x e to the root t dt. Well, okay, it's a chain rule, right? Because we have cosine x plugged into the function that gives you the integral from 0 to the independent variable of e to the root t dt. So how does the chain rule work? You take the derivative of the outside function, which is the integral. So the derivative of that would be e to the root whatever we plug inside, and whatever we plug in is the cosine x. So you get e to the root cosine x times the derivative of the cosine x, which is negative sine x. And that would already be the whole thing here. The only way this can get more complicated is if you have, well, not the only way, but one way in which this can become more complicated is that you could have variable lower and upper bounds, and we're integrating sine e to the t here. It's another one that you just want to stay away from. There is no closed form derivative, or if there is one, it's probably really, really hard to find. And so, well, I said this is the most complicated it can get. Well, you could also have an x inside the integral, but that's something we typically don't deal with in a first calculus class. So let's just deal with this one. Well, the derivative of this integral, where you've got variable lower and upper bound, well, the fundamental theorem of calculus only talks about one bound variable, namely the upper bound. So this we need to first break up into two integrals where only one bound is variable. And certainly this is the derivative of the integral from 0 to x plus the integral from negative x squared to 0. This one we can directly apply the fundamental theorem of calculus to. This one has a variable lower bound rather than a variable upper bound, but we can flip that, right? So from here to here, we just do the same thing and realize that the plus integral from negative x squared to 0 is the negative integral from 0 to negative x squared. If you flip the bounds, your integral switches its negative sign. Now we can take the derivative. This one goes directly, that is a straightforward application of the fundamental theorem of calculus, because all we do is we plug the upper bound in, so we get sine of e to the x. And then we have minus, and here's again a chain rule, right? We first plug the upper bound into the integrand, because the derivative will be sine e to the whatever we plug in, and then we have to multiply with the derivative of the inside, because it's a derivative with a chain rule. And now the minus gives us a plus, so this ends up being sine e to the x plus 2x sine e to the negative x squared. And that's already the whole thing. And that's it. Now, remember, this formula we're not going to use very often in calculus, because we're going to make plenty of use of antiderivatives to evaluate various concepts. And it also turns out that a good bit of stuff in nature really cooperates with us very nicely, so that the regular, if you will, form of the fundamental theorem of calculus works out just fine. However, anytime you have to integrate something where the integral gets really ugly, if you just don't know how to write down the integral, or if it's even impossible to find a nice antiderivative, you can always use the fundamental theorem of calculus and just say, my antiderivative is the integral from 0 to x of whatever my ugly function is, and it's going to be correct. Now, of course, if you're taking a test and somebody is testing you on integration methods, then that probably won't get you too far. But ultimately, when you're doing some really deep theory, or when you're in an applied class, sometimes this really is the only thing you can do, and then this form of the fundamental theorem of calculus really becomes pretty much standard operating procedure, and it saves you from a lot of trouble otherwise. All right, with that, we've talked enough about the fundamental theorem of calculus. We're now ready to talk about applications of integration, but that's a different presentation. Oh, come on.